Let's discuss what else determines airflow rates in buildings. Ventilation rates refer to the amount of outdoor air that must be provided to a space. The total airflow into a room, which is called the supply air rate, is generally higher than the ventilation rate. In ventilation systems with recirculation, outdoor air is brought in, mixed with some indoor return air, filtered and conditioned, and then supplied to the room. This process ensures sufficient airflow for the heating and cooling system to function effectively. An HVAC system provides heating, ventilation, and air conditioning to a space. HVAC systems often rely on a portion of recirculated air to maintain indoor comfort, as conditioning outdoor air demands more energy, especially when it's really hot or cold outside. The downside to using recirculated air is that indoor air pollutants are also recirculated. Most systems will at least have a filter to remove some, but not all of the particles in the air, but most filters can't remove gas pollutants. Only ventilation with outdoor air will decrease the amount of all pollutants from indoor sources. This is why it's so important to use minimum outdoor air ventilation rates to ensure good indoor air quality. In certain ventilation systems, the rate of outdoor air intake may vary. Systems equipped with an economizer feature an outdoor air damper assembly controlled by a motor to regulate the ventilation rate. Typically, the motor maintains the damper in a static position to meet the minimum ventilation requirement. However, when the building needs cooling and it's cool enough outside, the outdoor air damper opens to 100%. This process enables free cooling, reducing energy consumption. Some ventilation systems use demand-controlled ventilation, or DCV, to dynamically adjust ventilation rates according to the carbon dioxide or CO2 levels in the space. As people exhale carbon dioxide continuously, its concentration in the space rises, particularly with increased activity. With DCV, the ventilation rate changes to maintain carbon dioxide concentration in the space below a set point, which is typically around 1,000 parts per million, or ppm. This approach conserves energy by scaling back ventilation when the space occupancy is below maximum capacity. In California, the building energy efficiency standards still mandate a minimum ventilation rate for spaces equipped with DCV systems. This ensures that indoor air pollutants generated inside the building are adequately removed. Let's revisit Table 120.1-A of the standards. You'll notice that the outdoor air rate is reduced to 0.15 cubic feet per minute per square foot for all building types when DCV is used. Let's consider our previous classroom example that had a floor area of 1,000 square feet. With DCV implemented, the minimum ventilation rate is calculated as 1,000 square feet multiplied by 0.15 CFM per square foot, resulting in a minimum ventilation rate of 150 CFM, much smaller than our previously calculated 450 CFM. Therefore, in this scenario, the DCV system will maintain a minimum ventilation rate of 150 CFM and increase the ventilation rate as needed if carbon dioxide levels measured in the space go above the set point. DCV and economizer controls can be integrated and work together to regulate the ventilation rate in a building. Typically, the system operates in DCV mode. However, during cold weather when cooling is needed, the economizer takes precedence and temporarily opens the outdoor air damper up to 100%. Once the cooling demand subsides, the system returns to DCV mode. The logic governing economizer and DCV operations can be programmed into a building automation system or contained within a local controller within the HVAC unit. These controllers, often referred to as economizer controllers, require connection to an air temperature or enthalpy sensor for economizer functionality. Additionally, they often can support DCV functionality when connected to a carbon dioxide sensor within the building.